Magnetism. We are finally at magnetism. And luckily, most of us have played with magnets. So we know that a permanent magnet has two poles, a north pole and a south pole. And if we take that permanent magnet and put it near another permanent magnet, and we put the like poles together, we know that those like poles repel each other. Similarly, we could put the north poles together and we would get repulsive forces between these two magnets. And if we put opposite poles together like this, we get an attractive force. We know that magnets can exert forces on each other at a distance. And our model for how this happens, right, we used it when we had gravitational forces. We came up with a gravitational field. We said that that's how these objects could interact at a distance. There was a gravitational field around a massive object. And we did the same thing with electric charges. We said that there was an electric field around these charges, and that's how they could interact at a distance. And we can do the same thing with magnets. But now we can actually get a visual image of these fields, because we can take little tiny magnets and sprinkle them all around a big bar magnet, and they will align with the magnetic field lines, and we can get a visual of what those field lines would look like. The magnetic field lines look something like this. At first glance, it appears that this is similar to positive and negative charges in electric field lines, where the magnetic field lines originate on north poles and terminate on south poles. But they actually form loops. If we zoom in inside of the magnetic field lines do not point from the north to the south, like they would if they were positive charges at the north end and negative charges at the south end for an electric field. They point along the magnet, completing the loop. If we put two poles together, like these, opposite poles or like poles, we roughly get magnetic field lines that look like this. Magnetic field lines want to form complete loops. Now let's take our bar magnet with a north pole on the left and a south pole on the right and break it in half and see what we get. Do we get all the north poles on the left? Have we isolated the north poles and all the south poles on the right? This is not what happens. We don't isolate all the north poles on one side and all the souths on the other. What happens is we get two smaller magnets. With north and south poles. And we can break one of these up. And we get two smaller magnets with north and south poles. And we can keep going. And we always get a north and a south pole together. In physics, we say there are no magnetic monopoles. At least we haven't found them in nature. There are some theories that predict they exist, and I believe they've even made them materialize in labs for short periods of time. But in nature, we have not found a magnetic monopole. Whenever we find a north pole, there's a south pole right there with it. They come as a pair. And as we break up our magnet into smaller and smaller pieces, we just keep getting smaller and smaller magnets with a north pole and a south pole. And if this magnet is a chunk of iron, and we keep breaking it up smaller and smaller, eventually we could break one iron atom off of this magnet, and it acts like a magnet with a north pole and a south pole. There are some particles that act like magnets, like the electron. It acts like a little tiny magnet with a north pole and a south pole. Even our Earth has a magnetic field associated with it, as does the sun. Let's take a look at the Earth's field. It's as if the Earth is a bar magnet, and the magnetic field lines would look like the ones I drew earlier for a bar magnet. If this is our north pole of the Earth, which end of the magnet is this? The north pole or the south pole? That is a magnetic south pole, and the north pole will be down here. And the reason we call it the north pole is because our compass needle, when we hold a compass over here, the north pole of our compass, which is a little magnet with a north and a south pole, the north end of our compass points toward the north pole of the Earth. So the north pole of the Earth must be a magnetic south pole. So these lines, if I put arrows on them, would look like this. Now, the magnetic poles on the Earth change periodically. They flip. And it doesn't happen very consistently. It's roughly every 250,000 years. But those poles flip periodically. Now, the sun also has a magnetic field associated with it, and those poles also flip. And they flip very consistently, about every 11 years. One of the first questions we want to answer is, how are charged particles affected by magnetic fields? If we have a uniform magnetic field in this region of space, I'll have mine pointing to the right. And this is our magnetic field, and we use the symbol B, a capital B, to indicate a magnetic field. And I have a charged particle sitting here, charge Q, sitting there at rest in my magnetic field. It turns out there is no force on that particle. It is not affected by the magnetic field. Now, if I take that particle and I give it a push, so it has some velocity, it turns out there is no force on that particle from its interaction with the magnetic field. But if I take that particle and I give it a push in this direction, then there is a force. I'll call it F sub B for the magnetic force acting on my particle. What would that magnetic force depend on? It would probably depend on the strength of the magnetic field, right? This is an interaction between a charged particle and a magnetic field. It would probably depend on the strength of the magnetic field. It would probably also depend on the charge, right? If it's an interaction between a charged particle and the magnetic field, we would expect to see the charge having some impact on the strength of this force. And I've given you some hints here. It also depends on the velocity and the orientation the velocity has to the magnetic field. So we write it this way, V cross B. The magnetic force is equal to Q V cross B. This is a vector cross product between the velocity and the magnetic field lines. And the direction is given by the right-hand rule. If A, vector A, is vector B crossed with vector C, we take the tails of the two vectors, B and C, and put them together. And the magnitude of A is the magnitude of B times the magnitude of C times the sine of the angle you get when you put their tails together. And the direction is perpendicular to both B and C. It's perpendicular to the plane that B and C define. So it's either, in this case, B and C are in the plane of the page. So it has to be either out of the page or into the page. And in this case, it's out of the page. So as I'm looking at the page, if it's perpendicular to the page and pointing toward me, it's out of the page. If it's perpendicular to the page and pointing away from me, it's into the page. And how do I get that? I'm using my right-hand rule. And there are a lot of different right-hand rules. You can look them up. Some people take 3 fingers. The index finger would be your first vector in the cross product. And then your middle finger is the second vector in the cross product. And your thumb would be the cross product of those two. I like to put my fingers in the direction of the first vector. So I would put them in the direction of B. And then I kind of roll them toward the second vector, C. My thumb is the axis of rotation. So it has to be perpendicular to the plane defined by B and C. And B cross C, my thumb points up out of the page like this. So I get out of the page. What would happen if I flipped the order? What would happen if I came up with another vector? I'll call it D. I did C cross B instead of B cross C. I flipped the order of the two vectors. B is the same. C is the same. The magnitude of D is equal to the magnitude of A. But what's different? The direction is flipped by 180 degrees, because when I put my fingers in the direction of C and roll them toward B, my thumb points in the opposite direction into the page. So that means that the vector D is the opposite of vector A. Or I could write it this way. B cross C is negative C cross B. Remember, we're talking about vectors. That negative sign just flips the direction 180 degrees. The units for magnetic field are Tesla. Capital T is the symbol we use. The Tesla is the unit for magnetic field. One Tesla, if you look back at our equation for force, magnetic force, you could see must equal a Newton over a Coulomb meter per second. That's the same as a Newton over an amp meter. And another unit we use for magnetic field is the Gauss. People often use Gauss instead of Tesla, which is our SI unit, because it's more convenient. The Tesla is a fairly large amount of magnetic field. So in ordinary situations, you're dealing with much smaller quantities. It makes sense for people that work with magnetic fields a lot to use a different unit that's more appropriate for the fields they're using. And a lot of times you'll see people that work with magnetic fields use Gauss instead of Tesla. But when we use our equations, we need to use Tesla so the units work properly. As you may have guessed, we are now working in 3 dimensions. Because this vector cross product gives us a force that's perpendicular to the plane defined by the magnetic field and the velocity, we're going to have our particle moving perpendicular to that plane. We have to be able to draw in 3 dimensions and indicate the directions of the forces, the velocities, the magnetic fields, etc. Well, we do that using dots and crosses. So for our vectors that are in the plane of the page, we just use arrows like we always have. But if we have a direction that's perpendicular to the page, we indicate that with a dot or a cross. And the dot means it's coming out of the page, and the cross means it's going into the page. And the way to remember that is that it's like an arrow coming at you or going away from you. If somebody shoots an arrow from a bow and arrow toward you, what do you see? You just see a dot. You see the tip of the arrow coming toward you. But if they shoot it away from you, what do you see? You see the crosshairs on the back of the arrow as it moves away from you, the feathers on the back of the arrow, and it makes that little X. And so that's the way to remember. Is this coming toward you or going away from you, out of the page or into the page? Let's look at a few examples and see if we can determine the direction of the magnetic force on these charged particles moving in magnetic fields. In this case, I've got a positive charge moving toward the top of my page and a magnetic field pointing to the right. What direction is V cross B? I put my fingers in the direction of V and I roll them toward B, and in order to do that, my thumb has to point into the page, away from me. So V cross B is into the page, and QV cross B is into the page. In this situation, the magnetic field is pointing into the page. The magnetic field is perpendicular to the plane of the page, and our particle is moving in the plane of the page to the right. What direction is the magnetic force on this particle? Well, V is to the right. I put my fingers in that direction. B is into the page, and when I roll my fingers into the page, my thumb has to point toward the top of the page. So my force would be this way. I'll try not to use the words up and down. That can be very confusing here. I'll try to use the words top of the page, bottom of the page, left, right, into the page, and out of the page as my 6 directions. Now I've changed one thing. The magnetic field is the same, the direction of the velocity is the same, but I've changed this positive charge to a negative charge. What do you think that does to our force? Let's look at the equation. Our magnetic force is Q V cross B. What's the direction of V cross B in this case? V is to the right, B is into the page, so V cross B points toward the top of the page. But in order to get the force, we multiply by Q. And now we're multiplying by a negative number. And what does that do to the direction of the vector? It flips it by 180 degrees. So when we multiply by a negative charge, it flips the direction of V cross B, and so this force is toward the bottom of the page. Here our particle is moving in the same direction our magnetic field points. What's the magnetic force acting on this charge? The cross product gives us 0 because these two vectors point in the same direction. We're going to get a sine of 0 degrees. So this force is equal to 0. No force on this particle moving in the same direction as the magnetic field line. It has to have a component of its velocity perpendicular to those magnetic field lines to feel a magnetic force. Now we have a magnetic field pointing out of the page and a negatively charged particle moving toward the top of the page. So what direction is V cross B? V cross B is to the right. I put my fingers in the direction of the velocity. In order to roll them toward the magnetic field, my thumb points to the right. But Q is negative. I multiply that by a negative. So F sub B must point to the left.